I would like to introduce Professor Khalid Mosalam. Professor Mosalam is Professor of Civil Engineering and the Director of the Pacific Earthquake Engineering Research Center at the University of California in Berkeley. He has held many positions internationally, and he has been, for a number of years, a high-end foreign expert at Tongji University in Shanghai, in China. Khalid has a PhD degree from Cornell University, and also he holds a bachelor's degree and master's degree from Cairo University in Egypt. So we are very thankful to Khalid to join us in this seminar and give us a presentation of the current and future directions of hybrid testing and hybrid simulation. Back to you, Khalid. Thank you.
Oh. Good morning, everyone, and thank you for inviting me to MTS at Swinburne University and Riyadh for the introduction. I give a similar presentation to this one in the MTS peer workshop that was held back in March. I have a few new things to share, but the topic is hybrid simulation past and future. And for many years, my colleagues in Berkeley and myself have been involved in hybrid simulation with different funding sources from National Science Foundation, California Department of Transportation, Department of Energy, and also some international funding from the National Research Foundation of Singapore. And currently in Singapore, actually, in relation to these activities. Also, MTS has been a big supporter to our hybrid and other type of testing activities at Berkeley, and I thank them for that. Many of my current postdocs and former students have participated to the work on the different projects I am about to share with you. So as I said, back in March, we had this nice workshop organized by Pierre and MTS, and you see Graham Burnett and Michael Colton there. They attended our workshop, and we had some nice discussions, and I learned from them about this upcoming workshop, and they were kind enough, together with the other folks, to invite me to share this presentation with you. We had a nice group, we had a few demos, and this website that you see here now has almost 95% of all presentations, including the videos. So at the very end of my talk, I will just share one video with you by this gentleman here, Alex Mead, where he gave a demo. So I just do a 2-minute presentation of his demo. So is the voice okay? I kind of hear myself, so I just make sure the voice is fine.
All good, Khalid.
Okay, great. So the two main themes of this talk have to do with development and enhancement of several hybrid simulation systems for several applications. I'm not going too deep in any of these applications. I just want to share with you the breadth of the applications we have done over the years using hybrid simulation. And when I say we here, I just mean my own little group. I am sure there could be many other applications from my colleagues in Berkeley or in other institutions in Pierre or in other campuses in many places. The second theme is benefiting from hybrid simulation and performance-based earthquake engineering, which is the mission of the Pacific Earthquake Engineering Research Center, which I currently serve as its director. So, a brief background, we're all familiar with analytical simulation, and if parts of this analytical model would need experimental simulation or physical testing, then we form the so-called hybrid simulation or hybrid simulation model. And my association with hybrid simulation dates back to my days at Cornell in mid to late 90s. And my very first paper on the topic, at that time we used to call it pseudodynamic experimentation, was for this 2 degree of freedom system that I tested back in Cornell. And that kind of motivated the continuation of the work. We wanted to test this 2-story structure. We weren't sure what kind of load pattern to apply to the 2 degrees of freedom. And then we ran into some reports that my colleague, Steve Mahan, who unfortunately passed away last February, have done back in the 70s and 80s. And it kind of motivated us to adapt this method in this study. So taking this as an example, as I said, we're all familiar with analytical simulation, where part of this coupled equation of motion are treated as input, and this part is treated as output that's obtained by some kind of numerical integration. If we substructure this problem and the bottom story, let's say, is treated as a physical specimen, maybe some kind of a shear wall that is made of a composite material that we cannot model, as in this case, it is a structured insulated panel that is made of wood fitting and foam in the interior. So in that case, part of the model will be computed like the upper story, part will be measured like the lower story, and if we take the restoring force vector, is going to have that mix between analytical part and the experimental part. So, and then you go through the integration procedure and a few tricks here and there to control errors and so on. But the question is, why hybrid simulation and in such dynamic testing? Well, the idea of substructuring is very appealing because in testing a high voltage switch like this one on our 6 degree of freedom shaking table, switch is so tall, especially if the blade is open, and this is an important piece of equipment in electric substations. In an event of an earthquake, they control the flow of electricity, so they need to remain operational. And for us to do the test, we needed to create an opening in our ceiling, which cost us quite a bit of money, to be able to do one experiment. So instead of doing that, if this support structure, that's a steel frame, can be modeled in the computer, and the switch, which is made of porcelain material, can be put in our shaking table, we actually don't need such a tall structure and such a high expenses. So that's one obvious benefit. There are so many other benefits. Of course, we have to deal with issues now, not just putting the shaking as translational degree of freedom. We may need to worry about the rotational degree of freedom. But since we have a 6 degree of freedom shaking table, so applying rotations is possible. So for about 50 years or so, there is a lot of development that can actually take expensive shake table tests or less accurate quasi-static tests towards hybrid simulation, where you can achieve a compromise between cost and accuracy to be very close to accurate testing for dynamic response. You'll be also very close to the lower cost of quasi-static testing. So in the next 30, 40 slides or so, I'll just show you several applications that I was involved in that made use of hybrid simulation. I will give you an overview of the breadth of the applications. Similar to what I just described, testing electric equipment seems natural for substructuring, whether you do a 2D support structure or 3D support structure. This can be modeled in the computer, and let's say the insulator post or bushings or some other components that are hard to model can be tested physically. We may need to do the tests in real time because sometimes this material is polymer material, which are rate sensitive. We may need to do the test on a shaken table configuration rather than actuator configuration because the mass is distributed and you have infinite modes of vibration. So these are a series of 4 papers that describe in detail how we develop the system, how we do some parametric study on the system that I'm about to show you, and also how we enhance the control of the system, and then how we applied it to a variety of problems that deal with electric equipment. And we were hoping this will benefit code bodies like IEEE 693, which is the committee that developed seismic qualification of electric equipment in the United States. So the system is very simple. It has a data acquisition and control platform using the digital signal processor, DSP, where computations take place. The command displacement go to a simple controller, which then goes to the actuator, and then you measure the force feedback, and you keep doing that in time. This is a small unidirectional shaking table where we test one of those posts on it, while in the computational platform you have the support structure or any other elements we would like to model. So our goal is to be able to achieve one-time step execution in 1 millisecond, and this setup was able to do that. So now we take the conventional shaken table test of this 230 kilovolt switch. We can decompose it into an analytical substructure and an experimental substructure where we can make use of this system I just showed you. Some of the things we needed to take care of is some delays because of the time of computation or the communication. So in the past, we did a very simple feed-forward error compensation. There are much more sophisticated things you can do, but we were aiming towards also doing mixed variable control, where not just controlling displacement, but also controlling force. So estimating the error as a function of the velocity of the actuator has proven to be pretty reasonable. It does a good job in the majority of the signal, except of course at the peaks where velocity is 0 and you don't have error compensation. But there are so many other sophisticated methods to do that. MTS have done quite a bit of work on this, compensating for these delays and so on. So a few validations we have done on this exercise. On the left, you see the hybrid simulation, very simple physical specimen. On the right, you see the shaking table, which we can use that as a reference. And in terms of shake table results, how they compare with the hybrid simulation results, where shake table are much more expensive compared to the hybrid simulation. Comparison is very promising. Of course, if we go peak by peak, you see differences, but overall, you get pretty decent comparison with a much cheaper experiment to do. Even on local responses, like strain readings at the base of these posts, which trigger the failure of them, also we get pretty decent comparison with a much cheaper experiment to do. So how we do that to the next level? The Pacific Earthquake Engineering Research Center adopts this performance-based earthquake engineering framework where we calculate decision variables, making use of hazard analysis followed by structural analysis, by damage analysis, and then loss estimation. So I will interrupt the flow for a few seconds just to tell you a little bit about PEER. as some of you may know, PEER has its headquarters at Berkeley, and we have 17 campuses, 11 what we call the core institution, and 6 are educational affiliates. And we adopted this integrated performance-based engineering as our framework. And that's the same triple summation I showed you, but now as triple integral, where in the center we go all the way from engineering seismology to loss assessment. So over about 20 plus years, we have adopted this performance-based earthquake engineering methodology. Over the years, we developed several tools for that. OpenSeas, that many of you are familiar with. OpenFresco, which is of great relevance to this workshop, which is the open source framework for experimental setup and control. And also we have several databases for ground motion, for structural responses of instrumented structures, for components we have tested over the years. So you can find a lot of information about these things in our website. So going back to the problem we have at hand, so if we conduct now with simple hybrid simulation system, many tests, and we are able to plot some physical features of the system, like the support structure stiffness, if we vary that, and versus some response quantity, like normalized peak strain or peak displacement. These are all engineering demand parameters that we engineers can understand. But for decision making, we may want to convert that to some expected normalized economic losses. Then we can compare two designs, let's say using porcelain or using polymer insulator. And for that, we use this triple integral or triple summation, which again go from the seismic characterization to structural analysis, conditioning on the intensity measure, to the damage measure, conditioning on the engineering demand parameter, like these plots here, and then to the decision variable, which could be monetary losses or downtime, conditioning on this damage measure. And then use total probability theory, we can get the probability of exceeding a certain damage variable or decision variable. So in this work, we can take an electric substation, which we can characterize the hazard. We can identify critical components like these electric switches or some conductor cables between the equipment. And then we perform a variety of hybrid simulation modeling. We get the EDPs, we estimate the damage, and then we go to the loss estimation. We can even look at equipment interaction, where we can test multiple components. Some of them may be simulated, some of them may be physically tested. And then we can again come up with expected normalized economic losses if we have two designs, polymer versus porcelain, if we include a slack between the for the conductor cables between the equipment. Then decision makers, like electrical engineers who will decide on the design of this electric substation, can decide on what kind of slack we need between equipment, what kind of equipment material we could use for that particular substation, which will experience this particular hazard. So really, hybrid simulation can solve a much bigger problem without the need to do these expensive tests of always running the entire equipment on a check-in table, or without the need to do a large simulation with lots of uncertainties on how to model certain parts of the system. The rest, I'll show you other applications, but with less detailing. So we did an application of a reinforced concrete box girder bridge. We were interested to quantify the effective slab widths under lateral load. There are lots of work under gravity load, but under lateral load it's hard to decide which part of the bridge deck is acting with the bridge frame under earthquake loading, and then how retrofit can influence that. So again, we developed a substructure that we can test in the lab. It's tested in an inverted position for safety, And then you see some retrofits for columns, for example, using FRP racking, and then the rest of the bridge is modeled in the computer as a hybrid simulation system. Again, similar to the shake table system I showed you, here with the ESP card is able to connect to the actuators. The computational platform are already connected to OpenFresco, and then we connect the computational platform to the DSP, and then we connect the OpenFresco to the DSP with the PI interface, the Pacific Instrument Interface software. And then we have a system where we can put a computational substructure on OpenSeas. We can test this substructure of the bridge, and we are able again to vary different parameters of the computational model or test a variety of physical substructure in a rather inexpensive way. We also had another application that involved wind turbine. In the wind turbine blades, some problem always arise, which is some delamination that happened at the tail of the blade, because this cross section has its center of mass different from its center of shear. So you end up with quite a bit of torsion. So one of the things that you put some stiffeners here using these D strings, which are viscoelastic material that stiffen the end and prevents the peeling from happening. These blades tend to be very large. They are very important. That was collaboration with Technical University of Denmark, and wind energy is important, so we wanted to make sure that this blade would remain safe with that stiffener, that type of stiffener under extreme loading conditions. Similar setup was developed for that, but here the computational model was done using ANSYS, where the blade is modeled using shell elements, and the physical specimen was the D-string. That's proprietary material that we could not model in detail as part of the computational model. Communication is similar. You compute displacement to pass it on to the actuator, you get the force feedback, and you continue this process. The loading of this is actually gravity load when the blade spins, and we obtained a pretty good response that showed that the stiffener reduces displacement up to 75% reduction. So that was good results that we were able to obtain in a rather cheap test setup. A bigger project had to do with the analysis of the curtain wall system of Shanghai Tower. That's a very complex system. It uses cable where all the glass panels are hung from the cable. And again, we developed a conceptual model for these hanging cables, and the glass panels were treated as concentrated masses. And again, a very similar test setup that we used to study this problem. Another problem is what I started with, which are these structured insulated panels, which are composite panels, as you see here. And we wanted, again, to test it under earthquake loading. So we had a test setup that I showed you earlier, and we were able to vary lots of parameters without the need, for example, to build 2- or 3-story structure that we test in our shaking table. We can go down to testing parameters like the nail spacing and so on, and we try to optimize the system in a structural system in a rather cheap way without need to make gross assumptions on these composite panels and how to model them in the computer. So going back to the electric equipment problem, to show you another project that involved the equipment interaction, we test separate equipment. These are always connected by cables, and earthquakes, past earthquakes have shown that the interaction between the equipment can be the critical part. This switch yard in Winch 1 earthquake have totally collapsed because of this equipment interaction. So before we did that, we needed to do some development. Our system, which was part of the Network for Earthquake Engineering Simulation at Berkeley, used to deal with displacement commands that we communicate with our hardware. And then at some point we needed to do tests in real time on multiple shaking tables. And these equipment, some of them can be very stiff, some of them can be very flexible. So we wanted to do a better controller where not just control displacement, but we can control displacement, acceleration, and so on. So we use the MTS 3-variable controller where we can control displacement, velocity, and acceleration. And we extended that to use it in hybrid simulation. So if we look at, if the target is the blue, the target is red, displacement control is the blue using STS, the standard controller we had in the past. If we do 3-variable control, we can actually achieve a much better matching, especially in the range we are interested in. So we use that in doing the 2-shake table setup for 2 different equipment that are connected by a conductor cable. And we were able to put underneath each of these a support structure that can have different properties and run the test in real time so we can study this equipment interaction problem. We came up with interesting results. The procedure used in IEEE 693 can be unsafe in the sense that they don't consider the conductor cable in their equipment qualification. They just use a mass compensator, which may not be sufficient in terms of representing the cable dynamics. With hybrid testing, it was possible to quantify that better, at least to get better the basic response parameters of the system, like their natural frequencies and so on. So I'll show you now a few future directions. Some of them are we already working on. So hybrid simulation is certainly a viable method to do lots of projects with many applications. But we went back to the fundamentals to try to look at the problem of substructuring on a dynamic setting. So the hybrid system, as mechanicians do, you start with this potato-like domain, you decompose it into physical, which has the P letter here, and computational, and you try to introduce some gaps or mismatches at the interface to study the trajectory of the error in some kind of a normed space like N2 norm. And by varying the mismatch, this G function here, maybe varying the frequency mismatch or some other errors, we can study the problem and know when hybrid simulation ceases to give you good results. We applied that in several types of basic structural models that we have posed for solution for, like elastic or viscoelastic beams, and also elastic Kirchhoff plates. And we were able to get a good understanding of when that type of dynamic substructuring may not work very well, especially if we have some mismatch at the interface. So for the case of beam, we have this documented in this paper. We were able to see some spurious or parasitic peaks that are caused by the type of interface we introduce. So if the beam has a certain natural frequency, now with 2 beams with an interface or 2 substructures, you can actually excite some modes that are not real in the actual system that is not decomposed or is not does not include the interface. Of course, if everything is matching perfectly at the interface, you get the same results. But if there is some mismatch in these continuum mechanics problems, what kind of errors and how does it propagate So I was doing this work with my colleague Sanjay Govinji, who is a computational mechanics guy in our group. We also did that for plate structures, and we were able to see the same thing where you can actually get some modes that or that do not exist in the real system. We also have been using, I will close with this, have been using hybrid simulation for multi-physics problem. This is the work I'm doing here in Singapore, where we look at energy efficient buildings, and we focus on optimizing the design of the building envelope from thermal or optical considerations. So it's a big project that has variety of components. So I am focused on the thrust 5 that has to do with material design and life cycle. And it's a project that engaged the building, the grid, and the occupants, trying to come up with an optimum energy efficient building design. So just to look at how we use hybrid simulation in this context, if we want to test a variety of new facade systems, that's what we call complex fenestration, like new material, like here we were using these concrete panels with embedded optical fibers, so we can get all day lighting from the opaque part of the envelope. Then you can have a platform for computation like radiance, where you can simulate the indoor illuminance with a certain outdoor day lighting that's coming through this complex fenestration system. But maybe we cannot model this complex fenestration system in radiance, but radiance can compute for us the illuminance on the workbench, as architects would do, using ray tracing or computational fluid dynamic, whatever method is used for whatever physics you would like to mimic. So instead of trying to model these panels, we just test them in an outdoor cube, what we call it the cube, that mimic an actual building at a smaller scale, but the actual building is modeled in the computational platform using radiance. And then let's say if the lighting is too much, maybe you can bring the shade down, which will require some kind of controller, so you reduce the glare, and at some point there is cloud or the sun inclination change, so the shade will go up. So the simulation will keep going, similar to a step-by-step in earthquake loading, but here it's just in day lighting. Actually, this problem is much easier for hybrid simulation because the real timeness of this is not very demanding. It could be in terms of minutes rather than milliseconds, as we do in earthquake. But again, the notion of hybrid simulation can be very suitable for a problem like this. So the real building is modeled in the computer. The facade is physically testing. The two interact, and there may be some shading that will change the setting of the experiment, and accordingly will affect the interaction between the physical and computational domains. So here is an example where we demonstrate this by actually computational, where you can do some calculations in, let's say, energy bus. You have a simple controller in MATLAB, and I'll just show you this, where maybe the shade will be up if the temperature at a certain threshold. If you pass that, the shade will go down. And then, so if this is the outdoor temperature, then you make the calculations, determine how much heat we have, and then either you close or you open the shades, and that will change again the temperature calculations indoor, and this cycle will go on as we go. You can do that for the heat gain, or you can do it for the amount of lighting. Like if the light is too much, there is a lot of glare, you can bring the shades down until something changes, you bring the shade up, so you have that loop of physical testing of the complex facade, and computation of the indoor distribution of lighting or indoor temperature calculations. So instead of, I mean, again, the details in this paper, but instead of continue to explain that, I'll just show you this 2-minute demo on this website that I mentioned before, where we have all our presentations that we have from the previous MTS workshop.
Simple control law of looking at the actual horizontal illuminance that's calculated at the working plane. So if the working plane gets too bright, the shades are going to automatically deploy, and then when it gets less bright, they're going to retract. And again, this is just kind of a little bit of a contrived example to show you guys what was kind of the cutting edge of what we're working on. A different example might be some kind of geometrical changing facade, or something where you can apply a voltage and it changes the transmission properties. But with this, we're ready to go on the demo. So I'm just going to show you. What's going to happen over here is this is the cube. This represents the glazing condition. Often when you're modeling or measuring glazing, kind of at this level, you don't actually have anything at all. And then this right here is going to display in a moment when the code starts running the actual illuminance on that working plane surface. So we'll just get it started and we'll go from there. So it should be showing up. Okay, so you can see there, we're kind of at a very low lighting situation right now. So the floor plan looks very, very dark. But as we move up, you can see it's starting to get lighter and lighter. And eventually, we're going to overcome the threshold of what the control law has, and our window's going to shut. So you can see now the light's a lot less, So you can imagine maybe that was it's backing off now, maybe there's a big cloud coming over. And so the light's, a little bit less, and so the controller now says, well, it's not as bright, so we can open the windows back up, right? And maybe it comes back. And it shuts again, right? And then now maybe that's the end of the day, and so the sun's setting, and so we're gonna go back down, and you want to see those evening views, so the window opens back up. So you can imagine, the potential for a lot of these kind of scenarios really kind of explodes, and you get a lot of potential experiments that you can do.
So if you just download this video here, you will be able to see how some calculations in the background can control the facade opening and closing, which involve this physical domain of testing this particular complex facade, and how it's in conjunction with indoor calculations of the amount of illuminance, you can control the opening and closing of the shades. So this is also a hybrid simulation application for a different kind of physics, where when the shades go down, then the amount of light reduces until a next point in the day lighting exposure, then it may need to open again. So the demo that Alex Mead was demonstrating was bringing an artificial light towards the facade. If the light is too much, the shade closes. If he goes away from the facade, the light is less. Then the glare is reduced based on these calculations. Then the shade will be open again. So in conclusion, hybrid simulation is an economical and accurate testing method that can complement or replace shade table testing. Real-time hybrid simulation parametric study showed that hybrid simulation can provide valuable information which would be more costly and time-consuming in shade table testing. The benefit of hybrid simulation can significantly increase if it is coupled with performance-based earthquake engineering or performance-based engineering in general, where we can actually influence some specifications for code bodies, because we can run these experiments rather efficiently without the need to make gross assumptions if we do pure computation modeling, or without the need for highly expensive physical testing, pure physical testing. Hybrid simulation is conveniently applied to a variety of real engineering problems, ranging widely from interconnected substation equipment to bridge columns. The investigation of hybrid simulation using theoretical and computational mechanics provides considerable insight on the potential limitations of the method. So one has to be careful with how much mismatch happens between the computational structure and physical structure. Hybrid simulation has the potential to tackle problems involving physical phenomena, like the case of the wind turbine or the case of the daylighting simulation I have shown you. My last slide is I want to draw your attention to this website. And if you use, if you can scan this QR code, you can with your phone, you will get to this website, which is what we call the Phi Challenge, or Peer Hub ImageNet Challenge. So it's our way of introducing concepts of machine learning and deep learning in our domain of structural engineering, where we try to identify damage from images. So we're putting this out for the community to participate. So hopefully people from Australia or other parts will be able to participate. You can read a lot more about this challenge. At some point, we would like hybrid simulation to feed a lot of information to challenges like this, whether through images that we obtain from hybrid simulation tests that are conducted in Swinburne or in other campuses or other universities. With the help of NTS, hopefully we can bring some of these 21st century tools of machine learning and deep learning to structural engineering and physical engineering. Thank you very much.
Thank you, Khalid, for this comprehensive presentation. Just stay while we ask the audience if there are some questions.
Okay.
Any questions?
Michael has the microphone, so if anyone wants to ask a question, put your hand up.
Sean. Sean.
Hello, Khalid. This is Sean. Thank you for the wonderful presentation. And I have a simple question. In that wind blade test, I guess there are many stiffeners. So
Yes.
in the lab, there's only one stiffener tested.
Yes.
What about the other stiffeners? Do you model them, or do you use the tested stiffener property and apply to other stiffeners?
Very good question, Sean. There is something I did not explain because I knew it will take some time. We also had, so we had the model of the blade using shell elements. That's done in ETSIS. And we had only one stiffener tested, as you observed correctly. But we also had a model updating algorithm that take the results from the hybrid simulation and update the model of the other stiffeners, which only varied in size. They were just taller or shorter, depends on the geometry. So we kind of took a single stiffener experiment and we spread the results in real time to the other stiffeners, and then introduce the forced feedback to the computational ANSYS model. Some assumptions have to be made there. The best way is to test multiple stiffeners at the same time, which will require multiple setups. But these setups are very cheap and simple, which would have been very easy to do in a geographically distributed hybrid testing. If multiple labs have the same setup, they can test several stiffeners of different sizes, and we don't need to do this model updating assumption. But that's what we did.
Oh, thank you.
Any more questions, please? I mean.
Thank you very much.
Welcome.
Thank you very much, Professor Khalid, for your presentation. I have actually two questions. The first question is regarding the accuracy of hybrid testing. In the applications which you presented, perhaps these applications refer to low strain rates. And in terms of the filtration, what's your view about using hybrid simulation for conducting higher strain rate tests?
For the second question, I think it was hard to hear, but I think you asked about hybrid simulation for fire. Is that right?
High strain rate applications.
Oh, I see. Of course, the more complex the material you are testing, especially if you do it at a reduced scale, the more the requirements in you to do the test in real time or even faster than real time. So, for example, some of the base isolators that Steve Mayen have tested, he needed to do the test faster than real time, because when you do the scaling and if the material is sensitive to the loading rates, it puts very stringent requirements, and if you are incapable of doing that because of limitation of equipment or communication, the error will be high. I mean, there is no free lunch. So in most parts, maybe in Australia there is free lunch, but so of course the more complex the test is, the more difficult the material in terms of the loading, the higher the error will be. So we saw that in this computational exercise we did, where we tried to decompose a beam or a viscoelastic beam or a Kirchhoff plate, that it also brings some spurious frequencies that may not exist, especially if doing the test in real time. So I don't have a good answer for you, other than one has to be very careful in making sure that the sensitivity of the material to high rate effects is consistent with the available equipment to do the test in such real time. So if you're doing blast experiment or fire experiment, that puts a higher requirement in your equipment to do the tests that are with reasonable error bounds. But there are many studies that try to quantify the errors, and some good work in Lehigh. They done in different kind of dampers that are sensitive to the loading rate, and they obtain good results. But again, it depends on how good equipment you have.
Thank you.
Any more questions, please? Okay, if there are no more questions, I would like to thank Professor Mosalam. I know he's a very busy man, and we are very thankful that you shared with us this morning your expertise and your experiences with the various projects and what you see as the current and future directions in hybrid simulation. Much appreciated, Khalid, and look forward to future
Thank you very much, and I really appreciate you inviting me and accommodating my lack of presence. And I wish you a successful workshop. I'm looking forward to see the presentations when you have them posted. And please visit our peer MTS workshop, and hopefully we will put all the videos and presentations there soon. Majority of them are already there, and I wish you a successful workshop. Thank you.
Please join me in Professor. Thank you, Professor.